Today we're going to look at how to use our graphing calculators to determine activation energy in a chemical reaction. Now, we use something called the Irenaeus equation as our basis for doing this. The Irenaeus equation says that if you have the natural log of K, remember our rate constant, that's going to be equal to the negative of the activation energy divided by R, and notice that R is the joule R because activation energy is in joules, so we have to make sure the units are correct, times 1 over the temperature in kelvins plus the natural log of the frequency factor. Now, the frequency factor is the frequency of collisions with correct geometry and is given in units of liters per mole. We don't often use this particular equation, but if you look at how it's set up, you can see that it's set up in the form of y equals, I know we're most familiar with mx plus b, but remember our graphing calculators use a instead of m. So y equals ax plus b. The beauty part of this is that if we know the slope of a line that involves the natural log of the rate constant versus 1 over our temperature in kelvins, then that's going to give us a slope, and that slope is going to be equal to our negative activation energy over our constant R. That's going to allow us to calculate activation energy. I call this the negative ear slope equation. You've got to remember how to find this equation. It won't be on the AP test, so you'll have to know the equation. So negative ear slope just helps me remember what the equation is. So this is the equation we'll use once we graph the activation, or once we graph the information on our graphing calculators. Now, if activation energy is a smaller value, then K is going to be larger, so the reaction is going to go faster. If the activation energy is large, then K, our decay constant, is small, so the reaction is going to go slower. That kind of makes sense. The more energy that you have to put into the equation, the slower the reaction is going to go. So how do we graph this information? Well, let's say we did an experiment and we found this information. We determined the decay constant at different temperatures. Now remember, when we were doing rate law, we had to have everything done at the same temperature in order for those K values to be the same. But now we're dealing with a situation where we want to change the temperature values so that our K values will change as well. We can graph this information, get a slope, and be able to determine activation energy from this. Now, a couple of things. The first thing you want to do is to put temperature in L1, but remember, temperature has to be Kelvin. So make sure that you change all of these to Kelvin values. So this is going to be 293, 303, 313, 323, and 333. So make sure that when you put these into your graphing calculators, you put them in again as temperature. And T always goes in L1. So time for our rate law equations and graphing, temperature for our activation energy. We want T to be in L1. The K values are going to go in L2. I know this table is set up backwards, but I did it intentionally because sometimes they're set up backwards on AP tests or college problems or whatever, and you have to make sure that you put them into the correct list in your graphing calculator. And we already practiced doing this, so when you put it in the list, remember, you're going to hit Stat and then Edit. You're going to put your temperature values in L1 and your K values in L2. So that's what it should look like if you've put them in correctly. Now the next thing we're going to have to do is to come in, and what we were actually going to graph is 1 over T or temperature to the -1, however you want to write that. 1 over temperature, we're also going to graph ln of K. Those are the things that we're going to graph. So that's what's going to go in list 3 and list 4. Remind yourself how to do that. You're going to go to the tippy top, remember, of L3, and you're going to put in L1 and hit the reciprocal button on calculator. And when you hit enter, if you've done this correctly, you should come up with these values. So you can easily populate 1 over temperature, your L3 list, by simply doing it this way. You're going to do the same thing then to get L4 populated. You're going to go to the tippy top of L4. If I could say that better, it'd help. You're going to go to there and highlight that and type in ln of L2, similar to the type of thing we were doing when we were doing the graphical analysis of rate law. When you hit enter, then if you did it correctly, you should have these values, and this is what your screen should look like. Now, the nice thing about the activation energy calculation is that you don't have to go through graphing 3 different lines. All we want to graph is simply L3, comma L4. We're only graphing our 1 over temperature and our ln of K. So you're going to hit Stat Calc, remember, Stat Calc. You're going to go to Lin Reg, which is number 4, just like you did for rate law. And when you hit that, you'll come up with a screen that looks like this. Originally, it'll probably have L1 and L2 here. Make sure you change those. And then arrow down and hit Calculate to get those values. And when you do, your screen should look like this. We don't care about how good of a straight line it is. We're not worried about anything on activation energy except this one value, the value for slope. We need to know that the slope is negative 12,174. Just round it there. That's the value that we need to have in order to solve this problem. So once we know that, we can go back here. It wants us to calculate that. And we know that we have an equation of negative ear slope. So we know that activation energy, if we solve it for activation energy, remember our equation was that slope is equal to negative E sub A over R. When we solve that for activation energy, we get the activation energy is negative R times the slope. So remember the R value is 8.3145. And our value for our slope is negative 12,174. And when you multiply those together, it's going to be a positive number. Activation energy is always a positive number. When you add those together, it's going to be in joules. Remember, it's going to be in joules. We're going to change that to kilojoules, and we end up with 101 rounded to 3 sig figs kilojoules for our activation energy, and technically kilojoules per mole for our activation energy. So once we get everything canceled. So that's a calculation for activation energy using the graphing calculator. Now we can also use another form of the Irenaeus equation that looks like this. If we only have two values, please don't graph 2 points on a calculator because 2 points does not make a statistically good line. So this allows us to take two different situations when we have two different temperatures with two different K values, and we can figure out activation energy once again. The only thing we really need to keep track of is making sure that we keep K2 and T2 as a pair and K1 and T1 as a pair. So in this situation, it says that we have um, a colorless gas, dinitrogen tetroxide, decomposes to the brown gas nitrogen dioxide in a first order reaction with a value of K equal to 4.5 times 10 to the third reciprocal seconds at 275 degrees. So I'm going to make that 4.5 times 10 to the third our K1, which means that 275 is our T1. If K is later found to have a value of 1 times 10 to the minus or 10 to the fourth at 283 kelvins, what's the activation energy? So if this is K2, then this is going to be T2. So those are the values that we're going to be dealing with. Okay, using the equation then, we know that ln of K2 over K1 is equal to the activation energy over R times 1 over T1 minus 1 over T2. Plugging in our values, we get 1.00 times 10 to the fourth reciprocal seconds over 4.50 times 10 to the third reciprocal seconds. B sub A is what we don't know. Our R value, remember, is the 8.3145 joules per Kelvin mole. And our temperatures are 1 over 275 kelvins minus 1 over 283 kelvins. When you divide this, you get 2.222 equal to E sub A over 8.3145, again, joules per Kelvin mole. And when you subtract these two values, get 1.03 times 10 to the negative fourth. And solving for E sub A, taking the natural log of 2.22, getting that value, and then solving for E sub A, we end up with an activation energy. And practice going through this calculation to make sure that you can get this calculation. You're going to get the natural log of 2.22, okay? And then to solve for E sub A, you're going to multiply by the 8.3145. You're going to divide by the 1.03 times 10 to the minus fourth, and you're going to end up with 6.46 times 10 to the fourth joules per mole for the activation energy.